I was kind of I was trying to think what makes sense to do in this talk, in the last talk, and I you know, and I think I think I think the good thing would be, I thought that the good thing would be to kind of explain different questions that rise up from this. So the proof of the Weil conjecture is kind of I think you've seen it's extremely clever. It's kind of a very impressive sophisticated story, and it's in some sense a little bit too sophisticated, right? It's kind of you feel like someone is playing the trick is too clever, and this somehow was not and it's true. So and there's two things that you can say about this. So one is that well, first of all, the people who Delin and Grothendieck were not, Delin was happy to prove it, and everybody was happy that it was proved, but they were not under the impression that this is the correct proof. So this is one thing, and then another thing that should be said is that you can see that it's not the correct proof, or you can convince yourself it's not correct proof, not only by looking at the proof, but also by looking at what is still absent. Okay.
So when you say the correct proof, you mean like the proof of the Delin purity, or like even before that?
The proof of the Weil conjecture. The proof of the Weil conjecture. You would want
I think Shai asked like if you mean the Riemann hypothesis part, or also the just rationality and functional equation and.
No, I was definitely mean the Riemann hypothesis part, but I think that's not what Shai asked. Shai asked, do I mean the Weil conjectures as they originally stated, including the Riemann hypothesis, or do I mean the version with the lower shriek of tau mix is tau mix and the weights going down? I'm guessing that's what Shai meant, right?
I kind of asked about both, so.
Okay. So the answer is definitely the Riemann hypothesis. With regard to the lower shriek behavior of weights of the lower shriek, it's a little bit mixed because it is possible that the correct notion of shift shouldn't be the Eladic version of it. So yeah, you would want something like Delin's purity, but I don't know, maybe you would like it in a different context, which is maybe a little bit better behaved, and then identify it with the Eladic context. It's not entirely clear what you want in the case of the Delin purity. It's a little bit of a mix between the thing that you want and the thing that you have in some sense. So maybe who knows what would be the version. Some extent. Okay, so let's start by saying a few things about this. So one thing which is not known, and I already said it I think a few times, but let me just. It is not known. So what happened a priori? It's not known what happened when you vary L. Okay, so you have this number L, which is auxiliary, and you can change L between different primes, which are prime to P, and it's not even known that the Betty numbers are always the same. Okay, so
in which case, like if you assume that it is smooth and proper, then it is known, right?
Yeah, if it's smooth and proper, it follows from the Riemann hypothesis, of course. So why is it follow from the Riemann hypothesis? Because any infinite sequence that decomposes into a sum of geometric sequences decomposes the sum of geometric sequences in a unique way. So you can read the Betty numbers by looking at the eigenvalues that appear. And
but can't you take a resolution of singularities and stratify and stuff and make it always proper and
There's no resolution of singularities in positive characteristic. I think this is precisely the issue.
Okay.
That's a big part. So this is open, actually, and it's not even known. It's not even known if it's true, let's say, generically. Like you might say, okay, maybe there's a bunch of primes which are weird, but maybe we can prove that for every variety, for a large enough, they're all the same. Even this is not known. So this is the somehow one piece of the story, which is an example of something which is not known, and of course, the weights don't be. Now, how do we actually expect the weights to behave?
Oh wait, shall I suggest that I will write something like we agreed? So maybe I will. Okay, so okay, so I can write, but I cannot erase.
Okay, you can write, but you cannot erase. That's fine. I'll try to be perfect. Let's okay. So what happens when you don't satisfy properness and smoothness? This is another thing that I think it's important to say. So let's look at the I think it's a good idea to look at the first of a very simple example. So let's look at first at let's say it's GM, okay? Okay, and let's ask ourselves, so what are the okay, so I'm a little bit let's look at what happens for cohomology rather than compactly supported cohomology, just because I think it's going to be a little bit easier for people to kind of imagine in their head the situation. So how does the cohomology look like? So the zeroth cohomology of GM is of course, because it's connected, it's just QL bar, and since the Frobenius keeps these connected components in place, the action is by 1. That's exactly as before. Nothing happened. But what about age 1, the first cohomology of GM? So if we look at the first cohomology of GM with coefficients in QL bar, well, this thing is very easy. So this is also one-dimensional, right? It's a circle, but it's easy to see that it's with the weight twist 1, because this is the abelianization of the
1 or minus 1?
1. Oh, scheiße. Minus 1. So let's explain why. Let's try to understand what is the homology of GM. The first homology of GM, that's the abelianization of the pi 1, right? But we know explicitly all the covers of GM, right? This should be H1, not H0. And we know explicitly the covers of GM. All covers of GM, which are L-adic, prime to P, are just taking the L to the n power from GM to GM. So we see completely explicitly that the Galois group of the cover is being canonically identified with the roots of unity, which are the kernel of the map of GM. Okay. So in this case, we get that the homology is just the inverse limit of the mu m's, and they're nu L to the n, and therefore the cohomology is the dual of this. So, so this is the Q bar minus 1. So in particular, you see that the action on age 1 of the Galois is with respect to 1 divided by Q, right? Q to the minus 1. That's how. This is how the cohomology is being. This is how you are on the cohomology. No, I'm sorry, with Q, not Q to the minus 1, with Q. So you see that this seems like something that wants to live in the cohomological degree 2, but it lives in cohomological degree 1. Okay? And actually, you can write down, you can cover P1 by a copy of A1 and A1, which intersect in GM. And if you write the corresponding Meyer-Viatoris, you get an isomorphism, a canonical isomorphism between the first cohomology of GM and the second cohomology of P1. So you see that it's the same vector space with the same Frobenius action, but so the upshot that I want to make here is that the age one of GM wants to be the age 2 of P1. Okay, so you look inside, and you look inside the somehow the algebra. So you look inside the algebraic variety GM, and you find inside it, okay, a copy of H2 P1. Okay, and that should I do another example? Yeah, sure. Let's maybe do another example. So let's look at another affine variety. Okay. So let's look at the x cube plus y cube plus z cube equals 1. Okay, choose some field which is not F5, not F3. So, right. So, what is the Tal cohomology? So, F17, I guess. Not 9. Q. Oh, this is Q. So it's bigger than 3. Yes. Okay. So what is the? Oh wow. Okay. So what is this? What is the Tal cohomology of this thing? So once again, H0 is one-dimensional, and so by the way, affine varieties, the Tal cohomology stop at their own dimension rather than twice their dimension. This is known as Lefschetz theorem. So it is a general statement that is true in complex analysis. So maybe I should mention this because I think if you never see this, it might be a little bit confusing. If you have a system of equations defining a smooth affine algebraic variety over the complex numbers, and you look at the complex points, you would think, and you would correct that as a manifold, non-compact manifold, the dimension is always twice the algebraic dimension, because you look at complex points. But the homotopy dimension, it is always homotopy equivalent to a CW complex whose dimension is half of the expected dimension, which is the actual dimension of 1. So let's for example think about, if you think about an affine curve, for example, an affine complex curve, a complex curve, right? So if it's projective, then it looks like some some surface with some genus, right? So it's a 2-dimensional manifold, and it has second cohomology, so there's no way you can make it smaller. But if it's affine, then you do a puncture, and the moment that you puncture such a thing, it becomes a homotopy equivalent to a wedge of circles, which is a 1-dimensional CW complex. Okay, and that's a completely general phenomenon. Okay, so going back to the example that we had before.
Can I ask a small couple of questions? So first, can I ask 2 small questions?
Of course you can, yeah.
First, do you really need smooth here? You said smooth. Is it not true for singular stuff?
It's true for singular stuff,
okay.
But the proof is really different, so I was...
Yeah, because it sounds like you can kind of cut out. But so over the complex numbers, I'm only familiar with the proof using Morse theory. Can I ask for maybe like a couple of words about how one proves this for the Tal thing, or maybe even a...
So the proof of the complex numbers uses the using Morse theory, and wait, I actually don't remember about the non-smooth case in the Tal. I'm a little bit worried. Anyway, I don't remember right now. I don't want to try.
Okay, sorry.
No. But let me just answer your question. One way to prove this is this is related to what's called Lefschetz theorems. It has to do with the way that cup products with hyperplanes behave on the cohomology, and Delin just proved those theorems for the Tal cohomology. And this is
okay.
So yes. Okay. So let's look at this this example. So if we are so let's try. Okay. So the cohomology. How does the cohomology look like? So so this is a 2-dimensional thing. So H0 is actually of dimension 1. It's connected, and H1 actually has dimension 0, and H2 has dimension 8. Those are things that you just can compute using theorems from complex analysis and compare. Okay. Okay. So so now the question, so now the natural question is to ask is what are the weights that we expect to see? Okay. So the best way to understand it is the following. So first, consider the projective equation, which is the sum of x squared plus y cubed plus z squared minus w cubed equals 0. Okay. And what are we if we are trying to count the number of points on X, we can divide it into the points for which W is different than 0, or W equals 1. Those are the points on X, and the complement, right? And the complement here is an elliptic curve, right? So, so the number of points looks like the number of points on the this cubic surface minus the number of points on the elliptic curve, right?
Sorry, the elliptic curve is where W is different than 0 or is 0?
Where W is 0.
Okay, yeah, right.
Okay. Okay. So, in order to understand the, in order to understand the counting, for example, we can consider the number of points on this compactified space and the number of points in the complement. Right? That's what we are. That's the thing we are going to see. Okay.
Are you waiting for me to write something?
Yes.
What?
The oh wait, okay, I'll say another thing. Okay, so what is this X set? This X set is the is a cubic surface. Okay, so cubic surfaces have very simple kind of cohomology. Okay. They have the cohomology degree 0 is one-dimensional. The cohomology degree so the numbers, let me just say the Betty numbers. The Betty numbers are 1, 0, 7, 0, 1. Okay, this is
1, 0, 0.
No, 7, 1, 0, 7, 0, 1. Okay, so okay, so we are so if we are trying to look at the geometric sequence that correspond to this, right? So what do we have? We have a q squared coming from here. We have a 1.
Omer, there's a problem, I think. I think it should be 7 in both, right? I mean, what's going on?
What happened is that you removed the curve that and that added the this is added.
Oh, this was for the affine thing, the 108.
108 is for the affine.
Ah, okay. So there's no problem.
There's no problem. Okay. Okay. So okay. So what are the eigenvalues, right? So we have q squared in the 1 in the place that has the 1, right? So q to the 2n, the eigenvalues. That's it. So we have q squared in the place that there's a 1 there, right?
Well, what?
I'm trying to write down the eigenvalues that correspond to 10701, right? So the 1 corresponds to q squared.
This one?
It doesn't matter which. I don't know in which order you wrote it, but in one side you have q squared. In the other side you have 1. No, so the way you wrote it is the opposite. But doesn't matter. Right? The eigenvalue at the top is exactly q to the dimension. Yo, right?
I'm 1 second.
Sure.
Like this?
Yeah. There's a q squared there. Yes.
So it's not a cubic surface, it is a cubic surface?
It is a cubic surface.
Okay.
Okay, and we have the 1 corresponding to the 1, right?
Wait, but if it's of degree Oh, okay, fine. Yes.
So we have a 1 that corresponds to H0. That's another thing that we have. And the 7 is going to correspond to a bunch of things of absolute value Q. And in fact, you can prove that there was essentially Q times some root of unity. Okay?
Maybe this is a bad notation.
So without getting into without getting into too much. Okay, my point is, that's the point that I'm trying to make, is that you know, if you're going to look at the geometric sequence that corresponds to x hat, okay, you're going to look at the geometric sequence that corresponds to x hat. The thing that you're going to see there is going to be this, you know, the one going to cancel out because you get you get the one from x set and you reduce it from the elliptic curve, and then the q, right? So now we're going to subtract. So all of those things have positive. They're all positive because they live in even degrees, right? And now I need to subtract from it the thing that the elliptic curves give you. Okay. So the elliptic curves has a 1, which is going to cancel out. Okay.
What are you doing?
I'm trying to write down the sum of geometric sequences, which is the number of points on my affine variety. And I did it by compactifying this variety.
Yes.
And then trying to just say that it's the difference between the number of points. The number of points on U, it's the number of points in x hat times x.
Okay, so it's just x.
It's x, I'm sorry. The number of points in x are the number of points in the elliptic curve.
So this is this formula.
So I'm interested in the thing in the, I'm interested in the number of points on x. So I essentially told you how to look at the number of points on x hat. And now I'm going to subtract the number of points on the elliptic curve. Okay?
Mm-hmm.
So the number of points on elliptic curves are, and the first thing I wanted to say is that all of those eigenvalues add positively to the counting because they live in even dimensions. This is an algebraic variety that doesn't have odd cohomology.
Are you Lefschetz counting?
I'm counting. The only thing that I'm Lefschetz counting, but I'm just saying that I'm writing down a formula for the number of points on x hat. That's what I'm doing. Okay.
Omer, aren't all the roots of unity Q? You just blown up P3 6 points. Every blow up gives you Q eigenvalue.
You don't the blow ups. So it depends on which variety, which cubic surface you write, and which is the field. You don't. The blow up that you take is not 6 points which are defined over the base field. It is
if you take a weird point, then it gives you a, I get.
It's a permutation representation.
Yeah.
And because it's a permutation representation, then you get those
roots of unity. Yeah.
Those roots of unity depends on the field. This is, and which I don't remember how exactly. It's something that has to do with Q mod something. Q minus.
No, but that explanation was very good. Thanks.
Okay. So so now I want to subtract the thing that I get from the elliptic curve. Okay. So the thing that I get from the elliptic curve is I get a 1 because the elliptic curve also has the 1 in degree 0. I have Q in degree 1. You can write it below the below this free sequence. So E, no, not X.
Okay. So what to write?
So I have 1 that comes in degree 0. I have Q that lives in degree 2, right? And in the middle, I have two conjugate roots of unity, right? That comes in degree 1, and they contribute negatively. because they are odd. But I'm subtracting, right? So when I'm going to subtract, the following thing going to happen. The one going to cancel out. One of the roots of unity among those 7 is easy to prove that one of those is actually just Q. So it's going to cancel out with this Q below. And I'm going to I'm going to be left with this Q square and 6 Q up to root of unity, and alpha bar contributing positively. That's what's going to happen.
Positively, like it's in a plus sign, but it will be a negative number, right?
What, the alpha and alpha bar? They are not negative, not positive. Those are complex numbers.
Oh, yes, but the sum could be negative also.
The sum of alpha and alpha bar is we don't know about it. It's going to be smaller than the square root of Q.
When you said you meant the plus sign, not like positive. That
can be negative also, but it comes with the plus sign.
Yeah. So okay. So what do we see? So and there's Q. So Lior, there's also the Q squared to the D. Okay. That also appears. Okay. Okay. So now let's use Poincaré duality for something smooth which is not proper. So Poincaré duality tells us that the compactly supported cohomology of our variety, if we look at it, is going to be it's going to be one-dimensional in degree 4. It's going to be 8-dimensional in degree 2, and everything else is going to be 0, because we just need to take the thing that we wrote over there and do this. Okay.
For X.
For X, yes.
So have one dimension in degree 0.
Mm-hmm.
And 0 dimension.
No, it's
No,
0.
0 in degree.
It's 0, 0, 8, 0, 1. Right? It's you had 1, 0, 8, 0, 0, 0, 0, and you did. Okay.
Oh,
so,
okay. It's this one.
So you can read off now which eigenvalues sits where in this case, right? The Q squared eigenvalue going to live in the top. That's always the case. There's nothing to it. It's always the thing that's going to live in the top. And the variety that I chose for you was such that everything else has to be in degree 8. And you see now that it's not surprising that everything had positive contribution, because nothing can contribute negatively. The compactly supported cohomology in this case is all in even degrees. Okay. However, and that's the point I was trying to get to, if you look at this cohomology, the weights are 6 of the weights are correct, but 2 of them have the wrong weight. But it's not only that they, so you can say, okay, fine. So you showed us that the weights don't have to be correct. So what? But my point is different than that. That when you look at the wrong weights, those are not just arbitrary weights. Those are weights. This is just a copy of H1 of the elliptic curves that lives there. So if you read what's going on here, what happened here, that I took a copy of H2 of my cubic surface. I removed the one-dimensional space out of it, which is indeed it's kind of a subspace that lives in it. And then I took a copy of the H1 of an elliptic curve, and I added it there. And this is 6 plus 2 is my 8. Okay? What are the two examples that I showed you are trying to suggest? We don't have time to do another smooth example. The idea is that.
Wait, so you're saying that X itself somehow knows about E?
Yes.
Or maybe not about E itself, but at least about the weights that come from it.
So the picture that Grothendieck envisioned is the following: that if you take an algebraic variety and you somehow linearize it, thinking about its cohomology, the cohomology needs to break down into pieces which are pure, and those pure pieces are exactly some cohomology of a smooth and proper variety. And what happens in a non-smooth and proper variety is that someone took pieces of smooth and proper, non-smooth and proper varieties and put them together in a different order. But notice that there's something very funny about it, right? The algebraic variety that I chose, if you look at it, you just look at this algebraic variety, it's completely unclear how is it known that the existence of this elliptic curve. I chose a compactification. There could be other compactification, but I chose one that I knew is especially nice, so my counting would be easy. And then I just deduced from the counting that the elliptic curve needs to be there. You can see the representation attached to this elliptic curve in this algebraic variety. But the algebraic variety, the elliptic curve doesn't live in it. It somewhat lives in the boundary of it, but it's not entirely clear in what sense. Okay? So that is the idea of a motive. The idea that somehow, this algebraic variety that I just gave you, the affine one, or one way to think about this idea of motive is that this algebraic variety, if you linearize it, inside you're going to find that it's actually made out of a copy of the H1 of the elliptic curve and a copy of the H2 of the cubic surface, all of those pure and nice thing, or a part of the H2 of the elliptic surface, not all of it, and et cetera, et cetera. Okay, that's the now, you might say, well, that seems to be quite a lot to deduce just from the fact that the two eigenvalues there appear. But you should notice that I actually don't have just one Frobenius here, right? For one representation. I can use any L-adic cohomology, and in all of them I'm going to get this decomposition somehow. So
you can also choose any prime, like large enough, and you get the same thing.
Yes, and I can also choose, in this case, if I think about this variety is defined over Z, I can do it for every prime, mod every prime P. And for all of those Frobenius, I'm going to get that there's one elliptic curve whose Frobenius in different primes decompose like this. Okay? So the upshot of what I wanted to say is that so we have two things here. One is that we can vary the L, and we should always get the same answer. Two is that somehow the answer seems to be made out of pure parts that are cohomology in a specific dimension of some smooth and proper algebraic variety. Okay, but somehow it's not entirely clear how to produce this elliptic curve from the algebra, from the abstract equation x3 plus y3 plus z equals 1. And in more general cases, it might seem a little bit even weird. So, and you can get those weird things that can happen. Okay. Okay. So what was Grothendieck's idea? So Grothendieck's idea was to say, well, there's some cohomology theory, which is universal, the motivic cohomology, that for which things live in that cohomology theory, and for it there are certain conjectures that are being satisfied, called the standard conjectures, and those conjectures imply that would give us everything that we want. And the problem is that those conjectures are not known in general, not only not for the universal possible cohomology, which is not known how to be defined even, but it's even not known, those conjectures generally are not known for example, a Tal cohomology. So, so you really somehow not in a situation in which you know everything that you would want. But I think the thing that people here was most somehow curious by were the algebraic the algebraicity part. So I want to say something about the way that the standard conjecture. I don't have enough time to say everything.
Also, and another thing, maybe a small question. We didn't actually prove, we stated it, but we didn't actually prove, at least I didn't, I missed it probably, that the eigenvalues are integers.
That they are integers. Yes.
Does it easily follow from the proof, or does it require?
Let me see what is that. The eigenvalues are integers. Okay.
For the ones in the formula for the number of points, it follows because the sum of powers is in an integer.
Yes.
It's not obvious, but it does follow from that. And for in general, I don't know.
That's cool. Yeah, I'm spacing out about this. Okay, so let me now tell you something about Grothendieck's vision for, you know, how would you expect to get those polynomials which are rational? Okay, that's the and the so you have this trace of Frobenius, you have this characteristic polynomial of Frobenius, okay, and the characteristic polynomial of Frobenius, you know, is a priori an Eladic polynomial. And you might ask, why would you think that this Eladic polynomial has rational coefficients, okay, which are furthermore independent on L, or independent on whatever cohomology theory you would choose? And so how are you going to think about those numbers as the determinant of the Frobenius acting on some cohomology? And Grothendieck's idea was the following: is that those numbers are actually intersection numbers. So inside algebraic varieties, you can take algebraic cycles, okay, which are essentially sub-algebraic varieties or formal sums of such. And an algebraic cycle has a canonical class that lives in H, you know, if it's of dimension D. So it has a canonical class that lives in the cohomology H2D, right? And I'm sorry, if it's, what do you say, dimension or codimension? The codimension is I. It has a class that lives in H2I. Okay. You can for I being, so I is the codimension, not the dimension. Okay. And you know, because those are algebraic, you can get if you have things complement dimension, for example, you can intersect them, and this is going to give you something in H0. And this thing in H0 is a priori a number, for example, in QL for Eladic cohomology, but it's also just going to be an integer because it has an algebraic interpretation as the number of points essentially of the intersection. And because we allow our cycles to be formal sums or formal sums with rational coefficients, then it's going to be rational rather than maybe integral. But nevertheless, it's going to be a rational number. Okay.
So, Tomer, can I ask a small question to see whether I understand what you're saying correctly? So,
yeah.
Was Grothendieck's vision to kind of define canonically, independently of the varieties, some kind of canonical classes in the Chow group, such that if you compute some stuff out of them, you get the coefficients of the characteristic polynomial?
Well, it's not independent of the variety. It's something in the Chow group of the variety.
So for every variety, there are some classes, and so by independent of the variety, I mean something like chain classes of tangent bundle or whatever, like stuff like that, or
No. I'm going to be more precise in 2 minutes.
Okay.
Okay. So what is the essentially what is the idea? You're trying to think about you're trying to think about the Frobenius, and you can think about the Frobenius as if you think about the graph of Frobenius inside x times x. And you can look at the diagonal, which is another thing, and you want to try to say what happens when you take some power of the Frobenius and intersect it, and you take the fixed point. So this is exactly what Leo wrote. But let's say something about what is the graph of the Frobenius to the R. So here's an observation. Algebraic cycles inside x times x can be composed by convolution, because there's if you have 2 algebraic cycles in x times x, you can take the 2 maps from x times x times x to x times x, and you can pull back in 2 ways and then push in the 3rd way. So you can convince yourself quite easily that if the 2 algebraic cycles you compose are graphs of functions, then this composition is the graph of the composition of the function. Because essentially what I did here is say in the world of pull back and push forward, saying, give me A and B such that there existed C. So well, anyway, it's an easy thing to say. I don't think it's a good idea to say that. Okay. So the first thing is that this is so algebraic cycles can be composed, and furthermore, if you have a graph of a function, it gives you a map from x to x. But an algebraic cycle, general algebraic cycle in x times x, give you a map from the cohomology of x to the cohomology of x, because you can pull back, cap, and integrate. Okay, so we get this kind of a generalized notion of a function from x to itself, which is an algebraic cycle on the product of x and x. Okay, and for every generalized function in any reasonable cohomology theory, I get a map from the cohomology to the cohomology. It's worth noting that this map from the cohomology to the cohomology doesn't preserve degrees in general.
Which map from cohomology to cohomology?
So take a cohomology class, pull it back to x times x, cap it in the x times x ring with your cycle, and then push forward to x using the other coordinate.
And this is like multiplying by a kernel and integrating?
This is exactly like multiplying by a kernel and integrating. And you can see that, for example, if you take the graph of a function, then this thing exactly computes what the function does on the cohomology. But generally, it's a generalization of that. Okay. So okay. So in particular,
is this the proper case now? Or?
I'm sorry.
Is this the proper case?
Yeah, x assume that x is smooth and proper.
Mm-hmm.
Okay, so we're not going to worry about.
Just to be can you normalize my degrees? So if alpha is in what cohomology of x time, if in some cohomology of x time x, then by how many I shift the degree?
so if the dimension of x was
And
n, the dimension of x is n, as it's either n minus d or d minus n.
Should like plus d. I don't understand. The reasons comes from the alpha in the.
I cap with alpha. This increase the degree by d. But then I integrate with x. This decreases the degree by n. So it's plus d minus n.
Ah, okay.
Okay.
it makes sense because if alpha is the identity, it has to do nothing, right?
Yeah. So in the case that d equals n, if you're a graph of a function, then d equals n, right? Because the graph of a function is n dimensional. Then it becomes a map that goes from the cohomology to itself. Right? That's the special case. Okay, so so now if you look at the diagonal, okay, and then the diagonal lives in age nx times x, which lives in by Kunef, if you assume that we have Kunef, which is one of the assumptions of a Weil cohomology theory. It lives in the sum of age I plus age 2n minus I. Right? The tensor diagonal lived in this direct sum. Okay? So what happens if you, so let's denote by pi I the code, the class, the component of delta in that class alone. Okay? What happens when you apply pi I to the cohomology? Well, it's just acts as the projection from to age I. It kills anything which is not in age I, and it just acts as the projection. So the idea is that those pi, another way to say it, delta is the identity from age star to age star. So it's the sum of the maps, of the idempotent maps that kill all cohomology classes but keep the degree I map. And right, and those are okay. So yeah. So okay. So what the conjecture, the first standard conjecture of Grothendieck, we are now ready to state a standard conjecture of Grothendieck, is that pi I is representable. So right, so pi I is a cohomology class in degree n in x times x. Right, it lives in age I tensor age r minus I. It lives in degree n. And one way to produce such things is by taking some rational linear combination of algebraic cycles, of classes of algebraic cycles. So let's assume that pi I is algebraic. As a cohomology class, it is liftable.
Is it a conjecture or is it?
That's the conjecture. That's standard conjecture, and now I don't remember. I think, is it standard conjecture A or B or C or D? Let me actually look at. See, because I don't remember. Which standard conjecture is this? Okay, I don't remember. Anyway, this is one of the standard conjectures.
Well, quick question. The standard conjectures are for smooth proper varieties?
Well, the standard conjectures are, yes, essentially.
The phrasing of Grothendieck was for smooth proper, right?
Yeah, smooth and proper. This is, by the way, I just checked. This is standard conjecture C. So I didn't remember the number. Okay. So anyway, what would this imply? Okay. This would imply that what would this imply? This would imply that I claim that you can compute a trace of the Frobenius by the polynomial, the characteristic polynomial of a function by intersecting its powers with pi I. Because you have whatever this map is doing on you know, if you're trying to see what it does, if you look at what happened of this, you know, if you intersect with the diagonal, right, it counts the number of fixed points. But if you intersect, instead of intersecting with the diagonal, you intersected with pi I, it counts only the part of the number of fixed points that by the Grothendieck-Lefschetz formula would be related to the ith cohomology. So you would just get the geometric sequence. If you're just going to get the geometric sequence of that only the component of the geometric sequence that has to do with that specific cohomology. But this would imply that this is a series. This is a series of integers. So it means that, and the characteristic polynomial is something that if you apply it to those sequence of integers, is going to give 0. So by linear algebra, it means that it has to have rational coefficients. So this will say that not only, you know, this, right? So again, the rational coefficient would be implied by saying that not only the number of points on the curve is an integer, but rather that if you restrict yourself to the part of the number of points that correspond to a specific cohomology group, this still is an integer. That's what it says, right? And what Grothendieck said, well, I want those numbers to be reinterpreted, right? I can't say that the
not
number
an integer, right? A rational number, because it's a rational combination.
Yes, rational, but
okay.
In practice it's going to be an integer. But the level of precision that I'm doing here will always say that it's rational. So yes, rational. So Grothendieck said, well, if I was able to take this part, this pure, you know, the number of points. So, you know, you can think about this way. The number of points of an elliptic curve is 1 plus q, right, minus this alpha bar plus alpha to the 2d. This entire sum has a geometric meaning as an intersection. What if I was able to describe each of those things separately as an intersection? Then all of them will have to be rational, and then all of them will have will be algebraic numbers. And okay, then you can start. Okay, then you have some jump start to try to, you know, you related those things to intersection numbers, and then I have minus 1 minute, but you will be able to now, by saying things about the way that algebraic cycles behave, you will be able also to bound those things and etc. etc. So okay, so let me just say 2 more things. It took a little bit more than I wanted, but so note that this pi I, the way that it acts on the cohomology is an idempotent. So this suggested the following construction. Take the category of smooth and proper varieties, and such that maps between them. So it's not the category SM. It's a new category. Objects are smooth and proper varieties. But a morphism is a geometric cycle on x times y. It's an algebraic cycle on x times y. Now take this thing and idempotent complete it. If Grothendieck's standard conjecture C is true, it means that after you idempotent complete this, you can find inside objects that represent a specific cohomology, a specific piece of the cohomology of your algebraic variety. So in this idempotent completed category, you have those motives, those pieces of a smooth and proper variety that are only lives in degree I and can move around, like the H1 of the elliptic curve over there, that can suddenly be part of the two-dimensional cohomology of another variety. And then you would want to somehow enlarge this category to contain non-proper things, and you would want to say that just in this category, you know, it's just true that this variety that I wrote, xq plus yq plus zq equals 1, it is really just what it is. It is really somehow just the sum of the trivial motive. It's a motive in degree 2. I'm sorry, the Q2 motive, which is just state. You know, it's the same one that you just get in every algebraic variety of degree D. There's something that contributes the Q to the D, and then there's some part of a cubic surface. So it's turned out that the H2 of a cubic surface actually decomposes even further. So there's a 6-dimensional part of the 7-dimensional part that is also just now an object in this category that you get by splitting an idempotent on this cubic surface. And then you take the elliptic curve and you split its idempotent that leaves its H1, and you get some kind of an equation. In this category, you should just see that this object just decomposes into these pure parts that don't decompose any further. And then questions about, the questions about the behavior of those, of the polynomials there are really questions about, about intersection numbers of algebraic cycles. So I didn't have time to say how do you get the Riemann hypothesis. So let me say very quick thing about that. I don't have time to kind of explain exactly how, but the algebraic statement that you want is the following. Let me just say what it is. If you have a smooth and projective variety, you can take a hyperplane section that gives you a class in H2. And what you would, and you can cap with this class I times. So this is no, the codimension is 2. The codimension is 1. So there's a class in H2. There's a class in H2. Okay. And capping with this class, I times gives you a map from age I from age n minus I to age n plus I. And there's a theorem, and there's a hard-Lefschetz conjecture or hard-Lefschetz theorem that says that this is an isomorphism. Giving this, note that this is a different isomorphism. So this is an isomorphism. Note that those vector spaces are also dual to each other via Poincaré duality. So you get an isomorphism, natural isomorphism of a vector space with its dual, which allows you to put a certain scalar product, and then you show that that the existence of this scalar product make it so that the action on pure parts, all the eigenvalues have to have the size q to the I divided by 2, because if you divide by this q to the I divided by 2, you get something which is orthonormal with respect to this canonical scalar product. I'm not being very precise here, but I just wanted to tell you this is the piece. That's the piece that gives you the Riemann hypothesis.
Is the hard-Lefschetz one of the standard conjectures?
Yes.
And was it proved by Delin, or was it proved? Sorry.
So so eladically it is known. By the way, it's known as conjecture B. And so no, I actually maybe not known in general. I think even no, I think I'm suddenly spacing out, so I'm not remember. I think it is. I think it's not known in general. It's known for curves and a billion varieties and smooth varieties, which are complete intersections in the projective space and all the kinds of things. But, I think probably not in complete generality.
Yeah, the standard conjecture of Lefschetz type is highly not known in general.
Yeah. Not in.
Can I ask a question?
Let me say one last thing.
Go.
Okay. So this is the story of somehow how the motivic picture, from the perspective of how the motivic picture should give us a more conceptual explanation of the Riemann hypothesis and those polynomials, etc. It's just numbers that come from intersection numbers. There's kind of a different, if you will, perspective that was more successful on how to think about those things, about the relations between different L's that appear, and is to say, well, this is we can take all of those L's together and think about them as a compatible family of local systems for different L's, the cohomology, and kind of ask, what happens if you have such a compatible family, such that so the Frobenius eigenvalues are all the same, if you will stick to the point, and you can kind of try to study those kinds of algebraic gadgets, a collection of local systems that have this nice property that the Frobenius eigenvalues are the same when you choose the fiber, although they live over different fields. And the attempt to systematically, one way to call the attempt to systematically understand those things when you live over a curve is the Langlands problem. Okay. Anyway, I don't have enough time to talk about the Langlands problem. But the somehow you can try to use you can try to kind of say, okay, I'm not going to try. Okay. You can kind of try to go in both directions. You can try by saying, okay, let's say I have something very universal, that's the motivic story, right? And kind of construct something universal, and there's a Voitsky approach, and this retracts of smooth and proper things approach, and things like that, and try to say, well, what do I want from the universal thing to satisfy in order to prove everything? That is one approach, and that is somehow very inspiring, but was not extremely successful. You can take another approach. Another approach is saying, okay, I have this bunch of cohomology theories that seem to do the thing that I want, and there's more than just the Eladic ones. You can also have a crystalline version and things like that. And I can just take all of them together, say what all the compatibility they have, and axiomatize this, and try to say there's things that I can say about such a priori extremely weird collections of compatible representations or compatible local systems. And although maybe this approach seems more naive in some sense, it was extremely more successful. And this is one way to start thinking about what the Langlands problem is about. I'm going to stop here.
Okay, so thanks, Tomer.
Thanks.